Yes, but I don't know the zero. I don't know what why is there no student for
when you're not, you can't based on what I'm
Okay, listen. So as stated here, I mentioned when we gave the first test, it was 80% of your grade. It's the only test for this term. I sent out in a text and explained that if you had scored 82 or higher, there would be an opportunity for extra credit to get you to an A. Okay, as long as you're getting your homework done, that sort of thing. So this is the extra credit opportunity that I promised you would have. Okay, a lot of these, in fact, most of these problems are just old homework. So to get the extra credit points, what you have to do is on separate paper, one side of each paper only. So you don't write on front and back, just one side. You're going to work out problem by problem. Okay, it's got to be neat, organized, easy to follow, easy to understand. You can't just show an answer. You've got to give a reason. Okay. If you do that, and then you turn it in on the due date, there's no late on this one because it's just extra credit. Okay, like I always take individual circumstances, yes, but in general, if you don't turn it in on this date, you just miss the chance for the extra credit. Got it? Okay, each problem, if worked correctly and the grader can understand your reasoning, like it's easy to follow, is worth 2 full tickets. Okay? So there's 25 problems, so that means you can earn as many as 50 tickets here. Okay? Now, for those who already have an A, you're in a good position. You don't really need to do it. The tickets do not carry over. We don't actually use tickets in term 4. So anyway, this will be graded by students who are my TAs who had the class last year. And if they can't follow the logic, they won't give you points. And they're not going to hunt around. Like the instructions will be, if you can't understand what they've written, don't worry about it. Just no points, because it's just extra credit. Okay? Questions about what you need to do to get the extra credit. Even if you scored 82 on the test, this is enough extra credit to get you to an A. And if it's not quite, talk to me individually, because I promised I would give you the chance to get there. So, the term is fast ending, so here's the due date for having everything turned in for the end of the term. I've got to have a little buffer before the actual end of the term. So. Okay, cool. Pick up the pink, please. Go to problem 1. Okay, quick review. You've done a problem like this before where they gave you a region like this, and then it said find the area of the region. And remember how we did that? We said, well, let's put one rectangle right here, and let's find the area of that single rectangle. Like at 0.5, say. So we would say the length of that rectangle is the y-coordinate at the top. So we tell the grader that we're going to use f of x as e to the negative x squared. So the length of this rectangle, g of x would be the other function. 1 minus cosine x. So the length of the rectangle is y-coordinate at the top, subtract y-coordinate at the bottom. And it's kind of dangerous to use the actual function, so I would probably just say f subtract g. Questions to that? So that's not new. That you've done that quite a bit already. Y at the top subtract y at the bottom gives you the length of the rectangle. We then want the area of the shape So we'd have to find this point. We'll call that B since we're using A for area. This last period turns out to be 0.942. So your area is going to be, we take length and we multiply by the width of each rectangle, that's dx, and we want to do it for 1,000,000 different rectangles. So that's why we use an integral. And then the integral takes care of adding up all the little areas to get the entire area. So you don't want me to talk more about that review of how to find the area. Okay, what's new today is they're asking you to find volumes of shapes. Okay, what's nice about it is the method we use to find the volume is really, really simple. You end up with a three-dimensional object that looks, say, something like this. Okay, 3 dimensions. Got it? And the way you find the volume is you slice the object in such a way that all the slices have exactly the same shape. So that's why I've created it in this manner, so that every slice is just a circle. Got it? You would not want to slice it the other direction, because you get an odd, weird kind of shape that's hard to deal with. This is easy, it's just a circle. To find the volume of this, it's the same idea as we did here. We didn't really find the volume of this shape at all. We found the volume of 1,000,000 tiny rectangles. Then we added up all of those tiny rectangular volumes to get the entire volume. Wait, if you need me to say that again. Cool. To get this, sorry, to get that area. To get this volume, same idea. We're really not finding the volume of what you see. We're going to find the volume of one slice. And then the next, and then the next, and then the next. Use a big S to add them all up. Wait, if you need me to say that again. Okay? So, are you comfortable that here?
Yeah, it's just volume.
No worries. So instead of finding, this area as we see it, we actually find the volume of 1,000,000 thin rectangles. The area, I'm getting the words crossed, sorry. Instead of finding the volume of what you see here, we're going to find the volume of 1,000,000 thin circular discs.
Is that volume going to be different than the top volume because the circle technically is?
Yeah, no, well said. Just like here, the area of a rectangle that sits right here, say, is definitely different than the area of the rectangle here. We don't really care. We just find all the areas, add them up. The volume of this is going to be significantly less than the volume of this. We just add them all up. It's perfect. 2 points. Anyone else? Okay, so finding this volume is really, really simple. All you have to do is find the area that you're looking at. So the brown area. Okay, now this area is totally different than the area we're talking about here. We're talking about volume now. So you find this area multiplied by that thickness will give you the volume of what I'm holding in my hand.
Say that again, sorry.
So to find this volume of this object, you find this area that you see. Multiplied by this tiny thickness will give you this volume. Finding this area, really simple, because it's just the area of a circle as if there's no piece missing. Then you find the area of the missing piece and you subtract them. That gives you the brown area. Wait, if you need me to say that again.
Well, in this question here, we try to find the volume.
So don't worry about that quite yet. They are asking us to find the volume. Don't worry about that yet. Make sure that this makes sense. That if I'm trying to find the volume of this object, I can do it one slice at a time. The volume of an individual slice is really easy. It's just the area of the brown times the thickness. The area of the brown is easy because it's just the area of one circle, subtract the area of another circle. Please.
That makes sense, but what would that look like on a graph?
I will show that in a minute, so you're
okay.
good. No, 2 points.
So, Are we gonna have to find an equation that finds the area of this circle or something like the little one?
No, it's perfect. So we'll find an equation that finds the area of this circle as though there's nothing missing, and then another equation that finds the area of the small circle. But really, if what I'm talking about in my hands makes sense, translating it to here goes really quick. So questions about this, like how to find this volume, how to find, the area of the circle is just pi r squared. Area of this circle, pi r squared again. Just this radius goes from center to out, so it's a pretty good size. It's from here to here. Pretty good. Little radius. Okay. So now we need to see how all that fits on this picture. So here's how it fits. The way they create a solid is they take this shape. Can I erase all of this stuff? Okay. They take this shape and it rotates about the x-axis. So let's use this. Okay, this isn't exactly the same shape, but it's a shape. And when they say rotate, what they mean is like spin it. So take this and spin. If you spin really fast, you would see three-dimensional object. You don't really have to visualize to solve these problems, but it does, you don't really need to visualize. If I spin this thing, it's going to look like this. Okay? So that's how you go from 2 dimensions to 3. Okay? You don't really care what it looks like. What's important is if you slice it, every slice is just a circle. We didn't even say that again. Okay, so every slice is a circle. When I rotate this thing, I have some software that's on the internet. Shows what it looks like. Okay, so look at your paper. And notice, here's the curve e to the negative x squared. Look at your paper. Make sure you correlate it. Here's 1 minus cosine. Nod if you see it. Okay. The red line is the axis of rotation. So when the shape rotates about that line, the three-dimensional object, just like when I did this, so the computer now is going to do this effect, right? Where I unfold it, you get this three-dimensional object.
So how do you know the rotation axis?
They'll tell you. So in this one it says it's rotated about the x-axis.
Okay.
So if we slice it up, can you see that they will be circles? So the shape of the object really isn't this, but I don't really care. I know that the shape of any slice is going to be this. That's all that's important to me. Questions? Please.
So is it hollow on the inside, or?
So, kind of. I mean, it is hollow on the inside. It doesn't go all the way through. Like if you pick this thing up, turned it like this and poured water in it, it wouldn't leak. Because the bottom is solid, right here. Okay.
It's like a volcano.
Yes, very much. That's actually a really good way to think of it. Yeah. The reason it's solid on the bottom is if you look at the two-dimensional image, when this rotates right down here, there's no gap. Like that's touching the axis. So it causes no hole to go all the way through the object. If the rotational axis were here, then there would be a complete hole all the way through. Because as this rotated, it would never close off the shape. 2 points? Anybody else? Awesome. Okay, look. Okay, all you have to do now is be able to picture this. You don't have to picture the entire object. Just one slice is good enough. Picture this here. So the axis of rotation is my pen. You see it? So the inside radius is from here to here. So on this drawing, the inside radius goes from here to here. If I were slicing somewhere else, like over here, that inside radius would be much smaller. So it's different at different places. We're not finding area, we just need to find that radius. The outside radius is here. So draw this on your paper now. Questions?
You just picked a spot.
Yeah, random. You can pick a spot anywhere. It doesn't really matter, Ethan.
So it's like g of x minus 0 for the inner circle and the inner radius.
Well done. So this brown line, y at the top is g of x. Y at the bottom is 0. So the radius of that inner circle, this one, and the size of this circle varies depending on where we're making the cut, where we're slicing. We're slicing way over here, we get a pretty good sized inner circle. We slice way over here, we get a very small inner circle. But the radius will always be, take the G formula, plug in the x coordinate where you're making the slice. That's the radius of that inner circle. Anybody else? Please, Ethan.
And will we rotate around other than x equals 0?
You will, but it's really not difficult if you just draw what we're talking about. You say, okay, here's the axis. So like if the axis of rotation is here, then the inner radius will go from here to here. And the outer radius would go from here up to here. And you'd say, oh, the outer radius is f subtract negative 2. The inside radius is g subtract negative 2. Same idea. 4 for Ethan. Questions? Didn't want that one, I just wanted to go backwards a little bit.
So why is it so is g of x subtract subtract 0? So what is that? Like what is 0?
So 0 just is the fact that the top of the radius is found by using the g of x formula. The y coordinate at the bottom of the radius is just 0. Yep, top subtract bottom. For Preston. Okay, cool. Your outer radius f subtract 0. Question. Solid. So now I'm trying to find, remember, memorize this formula, please. This is the thing they always test you on. The volume is always going to equal, we take the cross-sectional area, multiplied by the thickness of that area, do it many, many times, that gives you the volume. So that's how we find volume. Volume is always found by cross-sectional area, multiplied by the thickness of the area, do it repeatedly. Add them all up. So I need to find this area. Can't be simpler. It's the area of a large circle, subtract the area of a small circle. So my area of this disk is simply pi outside radius squared and pi inside radius squared. Anyone need me to talk about that?
So
So that little circle thing you drew, was that just your big one?
So I'm just trying to show you've got a big circle and a little circle. So for finding this, the area that you see here, the way you're really finding it is by finding the area of all of it and then taking away that much. So this is the area of everything. This is the area of that. Subtracting them gives you that area, which is what we want. Questions? 2 from Brennan. One little side comment here I forgot to mention. You can get help from me, you can use your notes, you can get help from friends, but eyes on me. If you put down an answer, like you show an explanation and it doesn't make sense to you, you're just, you're committing theft. Seriously, like you're stealing. Okay, you're taking credit for something that isn't yours. If you get help that makes sense to you, then you write down your solution, even if it's just copying my solution. If it makes sense to you and you honestly can say, nope, I understand now I didn't, but now I do, that's fine. But don't just copy. So, okay. We good here? Awesome. So the volume's going to equal this. Okay, all of this work was just me explaining. On the actual AP test, they're not going to really look at any of this. They're going to look down here and say, okay, integral starts at 0, goes to b. You do have to specify b like we had before, so I do have to say f of x equals e to the negative x squared, g of x equals 1 minus cosine x. You have to use your calculator to find the intersection and store that value. Always have the big parenthesis. You have pi f of x squared, subtract pi g of x squared, multiply by dx, and then get the value. Question. Do it on your, oh please, mine.
Why is f of x come up? Oh, okay, I see.
2 points. Do it in your calculator to make sure it works. Go check the answer in the back. Stop me if you have something you want to ask me.
First child.
I think it's charging. I can't quite see it.
Is it f of x just because it's f of x minus 2?
Yeah.
So if it was on negative 2, like you said, that would be f of x minus 2, right?
I don't think that minus negative.
Negative.
This is negative x squared.
legs under her legs. They're like in her legs. Sister.
It just like I don't get
Did you ever find out if you did this movie recipe like that's
Already, I did something wrong.
Well, it's always safer to use
you didn't square. See, wait, so my question was, you know what he did that whole thing, but then he said, oh, eraser. The only thing that was important was finding what B was.
safer way to do it.
That was not.
Hey, look up, please. All eyes on me. Listen, look. Come on. Look here. Tristan, look up here. Ollie, look up. Okay. Don't type this and this on your screen. It tends to cause mistakes. Instead, do it this way. So let's see. Second quit. Clear that off. So we go math. Can't remember, is it 8 or 9? 9. So math 9, I go from 0. I should have stored my intersection. I did not, so we'll cheat. Then just use y1 and y2. So you're going to go pi. Can't see. That's not it. So you go pi and then just y1. Squared. This way you don't need nearly as many parentheses, although you have to do type the right thing. You stupid machine. Like, not alive.
Take the 2 of them.
There we go. Boom. Then minus. Shoot. If you're using y1 and y2, you don't.
What's the name? No. You wasted what?
Mine's still different.
Boom. That's the classification.
Type it exactly like that.
I did.
Pretty sure not.
Come on, maybe I did. Maybe I didn't.
How many got this to work? Show me hands. Come on. Who got it to work? 2 point. Nick. I never.
Just find the volume, so we'll
I don't know how I'm going to change that That's a lot of like doing it.
stop it one more time. Question is, last fall took 7.
Why does that hurt? He's so
there's a bit of explanation on the above in the video. So any questions here? 1 point, what is it?
747.
Good job.
Okay.
Thank you.
You good?
Yeah.
Yeah.
Cool. Unplugged for me. So. All right. Next one. Okay, look. Okay, if it's an FRQ, the same shaded region, everything. So you don't have to rewrite B equals f of x equals g of x equals. That's done. Okay, they're asking you to find volume, but the way this volume is described is different. Instead of taking the region and rotating, this one says that the region is the base of the solid. So this is now the flat part of the solid. Okay. The cross sections, meaning the slices, are square. So they look like this.
How are they square?
Okay, so how the square is, this is the base, okay? The squares come out of the board. Like that.
Oh, but they're squares out again.
Right. So this shape, hey, come on, focus. Did you not get it to work, Nathan?
It's the same argument, but I have like the exact same thing said, so I don't know.
Now watch this first and I'll come look. You're good. Now let's see. You're good. You got yours to work.
Yeah,
Yeah, Elijah. No worries, we'll find it. It's just when you missed it. Okay, the slices come straight out of the board. Got it? So this slice would fit right there. This slice cannot fit here because it's not a large enough square. This square would fit, like, let's take a little one here. This one fits here. Okay, understand? Awesome. When you stack them all up, you get a three-dimensional image, kind of like this.
Oh, that looks good.
So this is a slightly different region, but same idea. They've rotated it so it's like the region is the bottom now. Like you take this and make it the bottom, stack squares on top of it. As you put in more and more squares, it becomes a solid object.
Do you understand what the concept is solid?
Question? Okay, so that's the volume we're trying to find. Again, you really don't have to visualize the object. All you have to visualize is the slice. So before the slice looked like this, now the slice is even simpler. It's just a square. So this particular slice, one edge of the slice would be right here. So again, you're going to find volume. Write this on your paper. Volume is always going to equal the integral of the cross-sectional area. So you're always integrating by. So when you want to find volume, you must visualize what does the cross-section look like. So this time the area is just a square. So it's just this dimension, call it L, squared.
Length times width times.
But square, so length and width are the same.
Oh, yes.
So let's see. It's just a vertical line on a graph. So it's y coordinate at the top, subtract y at the bottom. And then square that, so that's your L. That gets squared. And then want me to talk through that again? Thanks, Rachel.
Oh wait, that's the area. Never mind.
No worries. Then for volume, we just put it into an integral. Dave?
Why is it square?
So, are you comfortable that to find the volume of this shape, this weird shape, we need to do it one slice at a time? Are you comfortable that the shape of every slice is square? Okay. So to find the volume of one slice, we find this square area times this thickness. So this dimension of the slice is seen on the board. I can see it. I can't see this dimension, but I know what that dimension is, because the object is square. So that's why I took this dimension times itself. That's why it's squared.
When do you have to like specify the width also?
So the thickness, that's dx.
Okay.
It's perfect. That makes sense?
Yeah.
Please.
Because the problem before this was the same exact, like all the same equations and graph, does that mean you don't have to re-specify that f of x equals?
So you got it.
Okay, cool.
Anybody else? You didn't make computer work.
I'm working on it.
Still not. What did this become?
0.461.
How many got it to work? Show me your hand.
6 points.
3.
That's 6, but it's a 5 tally.
Oh, what the? Tom Jerry where?
One. Like the medieval one, where they like go like 3 lesson trains almost.
Oh yeah, that was the other
I mean, Jerry's one of them lost. Gray, light blue.
Okay, any questions here? Do number 3 and 4 on your own. Go. Do 3 and 4 on your own. The only thing that's different is they move the axis of rotation. It says the axis of rotation is the horizontal line y equal 1. Now, if this feels simple, then you've got it. If it feels complicated, we need to talk until it feels simple. I don't really care about the shape. All I really care is that when this volume is created, I know that every slice will be a circle because it's created by rotation. So here's my circle again. Raise your hand if you know where in this picture is the center of every slice. Just show me your hands. Come on. So where in this picture is my pen? Right here, the center of the slice. So where in the picture on the board is the slice center located? Zach?
the red line.
So how many knew that my pen corresponds perfectly to this red line? Show me your hand. 2 points. Okay, look. So again, all we have to do is find the area of this thing. Because you've memorized that volume is always going to equal the integral of the cross-sectional area. Area of a circle, pi r squared minus pi r squared. So the radius now starts here, goes to here. So one radius looks like this. That's 1 minus, I need to label these things. Let's call this upper one, as we often do, F. This one, G. So my outside radius will be 1 subtract G.
How do you know that's the radius of the outside?
So are you clear that on this picture, the red line is here? Good. Are you clear in this picture, the radius goes from here to here? So that's here to the outer edge.
Okay.
2 points. Anybody else? And then the inside radius would be here. And then it's exactly the same as the other two, so. See if you can do 5 and 6 as well, go.
I was looking at getting this. So this is the inner radius, and then this is the outer one?
No.
Or one?
So what happens is, we kind of have this, we have this weird thing again, right?
Yeah.
At this time it comes this way, like the axis is above, so it unfolds like this, right? So we have a solid like this, we have our slice, in the middle of the slice is that line like this. So inner radius goes from here to there, which is right there. So this is so this is an inside radius of one slice. This is actually an inside radius of a different slice. Correct. So both of these are inside radius. This is also inside radius. They're just depending on where we slice it. So if we slice it here, that's the inside of that piece. Over here, the hole is just bigger. The outer, so outside radius goes from here all the way to here. So like on this one, the inner is starting here, here, stopping right there. The outer is going from here all the way to here. Right, so that's why I said my...
It's the exact same. It's just the beginning part. It's like,
good job, Ashley.
kind of, but not really.
Some I understand this, but I don't think I can apply it anywhere else.
Hold on. Yeah. Talk to me.
I just don't understand.
So you're okay that whatever this volume looks like, we're going to cut it into circles.
Yeah.
It's spinning. Are you okay that this line?
Yes.
So, let's try to make it into like paper like that.
Yeah.
Okay. This edge right here is right there. So the radius of the cutout is if we rotated the paper straight up, it'd be like from here to here, but that's the same dimension.
Okay, so how come you have that?
So we did the same thing. Except now it's rotating this way. So the length of the line is still one at the top.
Okay, yeah. So you're just taking what's on the top? Okay.
So here, it's like that. But now the top is one,
And the
bottom is that right there.
Yeah, so I didn't watch my YouTube
Just This is what paper you grab. So is your f of x the y1 or the y2? When you type it in, what might you know what's up?
The R V shape reaches boundary. I'm gonna keep it up.
Score, good man. I knew I put your brother right there.
I know, no, she stresses me out, so does she, but like, because they're so freaking fast at this. But they also help those.
Good.
So I got the same negative as I
They're the same question.
You're not typing it.
Rectangle is like kind of
The radius is 1. So the line of rotation is up here. Okay. So
5 times in length is the base of
are you confident that this is where show me you got 6 to work. Show me who got 6 to work.
6?
Who got 6 to work? 2 more. Who has questions on 6? Awesome. Keep going.
Number 7.
Paste it 1 second.
I think so.
F of G F of X? That would be
Go to 10, please. Hey, move to 10.
No.
Double digits, please. Move to 10, please. One second while I get a copy.
I can't finish this in my mouth.
Okay. The only thing that's different about 10, listen, is that the slices, so again, you have memorized that you're always finding volume by integrating the area of each slice. Okay? The only thing that's new here is the slices have a different shape.
No.
No big deal. What are the slices shaped this time?
Semicircle.
Semicircles.
I know that.
So it looks like this. So here's your region. Look at it. You're going to stack on top of that region semicircles.
And we know the semicircle is part of the curved one.
Okay, look. So we're going to stack on top of the region this kind of a slice.
Where's this? How do we know it's a semicircle?
So it says here, the region R is the base of the solid. For this solid, the cross sections, that means slice,
Okay.
perpendicular to the x-axis, so the slices are oriented like this, are semicircles.
Okay. Cool.
There you go.
Wait, so it's not like out at you, it's like
No, it's out at you. It's still coming out. The semicircle looks like this.
it's placed like that. Okay.
Okay? Good?
But it says the diameters of the semicircle are also the same shape as that.
So the diameters of each semicircle go from F
Oh, that hurts you that it's that way.
to G. So this is the diameter of one semicircle. So this one's a little bit too big, but it fits like that. Is that better?
Diameter.
Okay.
Yes.
Diameter of the semicircle.
Because it's the same thing as like.
Like a full circle.
Yeah.
Perfect. You good? Are we good? Here's what the software would show that looks like. 1 second, sorry. Like that. Go ahead.
So if it says the diameter is extending from, no, never mind, I'll lie. Never mind, leave it out.
This one you can turn it so it kind of helps. Look. So that's what you see on the paper. But when you make it three-dimensional, it becomes that.
Like fish.
Okay? Half of a fish. We good?
Oh, it does look like that.
Like slice right down the center.
Yeah,
Okay. Ah.
great minds think alike.
Okay, look out. Come on. Look at me. I have a little trick. Watch. This will make the problem a lot easier. Come on. Okay. Everybody knows that the area of a circle is pi r squared.
Yes.
So the area of a semicircle is 1/2 of pi r squared. Okay? But in this particular type of problem, the radius is kind of a, I don't know, you can do it that way. It's no big deal. So let's just do it that way. So we got volume's going to equal, see, we got the radius.
If you have an easier way.
I'm not sure it actually is, to be honest. So we got F minus G, right? That's the, oh, that's the diameter. Back up. So the diameter is that. So the radius is just 1/2 of that.
Why is that the diameter again?
Because it says that the diameter of every semicircle goes from here to here.
Okay, yes.
It's good there. There we go. Awesome. So our volume is just going to be integrate from 0 to the intersection. We've got to do pi because it's a, well, it's got to be 1/2 pi times the radius, which is another 1/2. Oh, wait a minute, that's got to get squared.
No, okay.
Okay,
Because you've got to take the radius, squared.
So what's your other way?
but when you
Yeah.
when you put the half inside the parentheses, like, why do you need it on the outside?
6 times 6.
So,
Because didn't you get the 1/2 right
look,
here?
I've got to go
Oh, 1/2.
1/2 of pi times r squared.
Oh, okay. So you did the half to get the radius, and then you did the half.
Have to get half the
semicircle.
semicircle.
That's why there's 2. Okay.
Yep, look out. Okay, look. Okay, you're all seeing what I see as well. The half and lots of parentheses is causing trouble, right?
Yep.
Okay. The area of a semicircle is also pi over 8 times the diameter squared. That's a lot easier to type in. So just do this. Pi over 8. And then the diameter is just F subtract G. So you can do it either way.
Is that when you square and times the 1/2?
Right, because this 1/2 gets squared. That makes it 1/4. That 1/4 times the 1/2 makes the 8. So I like typing this because it's cleaner.
Square still stays there?
Because you still have to have the radius squared.
Wait, pi over 8 is what again? Is 1/2.
So look here. The 1/2 is being squared.
Yep.
So what's 1/2 squared?
1/4.
Good. That gets multiplied by another 1/2, which would make, that's where the 8 comes from. But I still got to square the F minus G.
Yes, but you said something. You said it.
What I said was the area of a semicircle can be thought of as 1/2 pi times the radius squared. But the area of a semicircle can also be thought of as pi over 8 times the diameter squared. So I like using this one because in these problems you see the diameter. So that's what I like. Good work.